This will be a short tutorial on how to linearize. So, as has been mentioned in class, when we get a set of data that is not already a straight line, what we want to do is make it a straight line. Now, there are a number of ways to go about this. A curve fit is one of the standard ways, and usually it requires some sense of what kind of fit might be best out of many different options. And this is one approach that we can make. But for the purposes of modeling instruction, we want to take a different approach that turns out to be a very powerful approach as well. And we want to somehow manipulate the nonlinear graph each time in order to make it linear. So for instance, the example that I want to take a look at is the following. So we have a set of data, and it really doesn't matter what the variables are. It could be the variable, the independent variable would be r in meters, so maybe a radius or a distance, and F would be our force in newtons. So here we have value for r, our value for F. And this could be representative of the Coulomb repulsive or attractive force in electrostatics. But it really doesn't matter what this is, it's the sample that we're looking for. So we have these values, and looking at the graph, what we see is this is not linear. In fact, if I would try to do a linear fit to this, it really doesn't look very good. So this is clearly not a linear set of data. So what I want to do is take this graph and make it linear. So I want to take a look at this data drawn by hand. So again, we have our data values here. And what I've done is I've drawn a very strange scale, and you'll see what's happening here in a moment. We see on this small scale that I plot each of these points by hand, and this is the curve that we saw in LoggerPro. But now what I want to do is I want to manipulate these points. I want to take this curve and make it a straight line. And what I need to do is stretch these points over to the side. Here's what I mean. If I can take, say, this point here and drag it over, and this point here and drag it a bit further, this point even further still, and this point even further still, what we find is that it looks like we've dragged all these points onto a line. But what function can we use so that we're not dragging the first point at all and each subsequent point gets dragged a little bit further? Well, one thing we can try is we can square the x variable so that 1 is squared to 1, 2 is squared to 4, and so on. And so what we see is what we have, the second point is at 4 up at 40, and then the third point is now at 9. We've dragged from 3 over to 9 at 90. We've dragged from 4 over to 16 at 160. And you can see this data set is rigged so that we have 16 and 160, 25 and 250. But it gets the point across. So that then when we fit a line to this, voila, look, this is a perfect fit. Even a rough sketch by hand on the board does a nice job of showing a linear fit. So going back to LoggerPro, how can we do that manipulation here? Well, we want to create a new calculated column. So we go to Data, New Calculated Column, and we will call this r squared. So we can either do r caret 2, or if we want to be a little more sophisticated, we can go to the drop-down menu, pick superscript, and go for the square here. And the unit will be meters squared. So we need to remember to square both the unit and the name. So now under expression, we are going to select what it is that we want to square. So one of the data sets is going to be the radius or distance r. So we select that, and then squaring is doing the caret 2. And what we see is a new set of data has appeared with all of the squared values. Now the last step we need to do is actually put this on the graph. So we go down here to where r is on the x-axis, and we choose r squared, do an auto fit, and voila, we have a straight line. So now we can do the linear curve fit. And I will make this a little bit larger so it's easier to see. And not surprisingly, the y-intercept is 0. Again, it's rigged data. But we get this value for the slope of 10 with a unit of newtons per meter squared. So noting that the unit here is meters squared now that we've squared the x-axis. The final step is writing out the specific math model. And this is going to take this form, so that we have the force in newtons is equal to 10 newtons per meter squared. That is our slope. And then we have to remember now our independent variable is squared, so it needs to be r squared times meter squared. So this now is our specific math model, and we can go on to try to determine what the meaning of the slope is and put together a general math model. And that is all you need to do in order to linearize sets of data that are nonlinear. And we have a number of different possibilities for that. In the workbook there is a handy key to give you some insight onto what functions to use for linearizing certain sets of data. And usually it's a handful of cases. You either square the x-axis, you might square the y-axis, or you might invert the x-axis. And those are the main choices that we look at. In the second semester we end up finding a few new and interesting cases that use the sine or cosine function, or have a number of different things being inverted. But for the most part, during Physics 110 or Physics 210, we're going to see some of the simpler cases that are quite easy to linearize. So hopefully this has helped, and if you have any questions, don't hesitate to ask.